Okay, so the last piece of the puzzle here then is to complete the cycle, come back to diagnoses, and figure out how they are identified on EKGs. And one of the recommended sites that I recommend would be EKGLibrary.com. So it's www.ekglibrary.com. I like it because it's all free and open access as long as I attribute them, which I just did. One of the other things I like that he'll take you through, author, is different EKGs. You can get all of these EKGs and you can look at all of these. But what I particularly like students to go through is the normal electrocardiogram, because it states right here that the diagnosis of a normal ECG is made by excluding any recognized abnormality. And so he'll take you through the steps. What he'll take you through are what you're looking for. And I'm not going to give you, obviously, again, I'm going to repeat what I said before. This is not medical quality information, let's just put it that way. It's educational. It's meant to be educational for community college freshmen, sophomore, pre-health majors. And so it's not going to be absolutely complete. It's just going to give you an idea, a foundation on which to explore more. One of the first things that you can look for is just a normal sinus rhythm. Is the heart rate too fast? Is the heart rate too slow? Bradycardia is when the heart rate is below 60. Tachycardia is when the heart rate is above 100. So it's clear the heart rate looks pretty slow. Now if you want to technically get the heart rate absolutely correctly, what you do is you take 60, and from 60 you divide 0.04 times the number of small little blocks between peaks. Now an easier way to do it, remember the sequence 300, 150, 100, 75, and 60. Divide from 300 the number of big boxes that separate the same feature in the EKG, and it's usually easiest to use the R peak to do that. Another thing to look at is QRS Axis, and this website takes you through some of the technicalities of QRS Axis. I also put up a video to explain QRS Axis, and one of the things you'll see right away is that I am simplifying this quite a bit. I just talked about QRS Axis in terms of infarct and hypertrophy, but there's a lot more that can be gleaned from the QRS Axis. I'm not going to go into these in detail. I'm just going to refer you back to that video. The next thing that the website will have you look at is the size of the P waves. And basically what you're looking for is you don't want too high of a P wave, because that can indicate hypertrophy. Same with the width. Both of those can indicate hypertrophy. So notice right here in lead 2, this is a really large P wave, and what that large P wave is saying is there's a lot of voltage during atrial depolarization, which means there's a lot of muscle. This could be some kind of stenosis, or in this case it was bronchitis, so that basically the pressure is building back up into the atria from the fluid in the lungs, stressing the atria and causing them to hypertrophy. One of the ways that you can kind of see this just on a normal EKG is you can compare the P wave in 1 versus 2. It's kind of hard to do this and describe this, but normally the P wave is bigger in lead 2 than it is in lead 1, because the normal vector is more parallel to lead 2 than it is to lead 1. If there's left atrial hypertrophy, that's going to shift that axis. It's going to become more parallel to lead 1, which is going to make the P wave in lead 1 then larger. So looking at the P wave can give you an indication about hypertrophies in the atria. Normal PR interval, again, it's kind of hard to describe this, but remember when we looked at the EKG, the AV node has a pause in it, and that pause is about 1/10 of a second. If you don't have that pause between the P and the R, it means you're not going through the AV node, you're bypassing it. And Wolff-Parkinson-White is kind of a classic, where the current does not go through the AV node. It's found another method, an alternate pathway from the atria into the ventricle, and that's why this interval between the P and the Q is very, very short. Didn't go through the AV, didn't get delayed by the AV. Now another thing that can happen, not only can the PR become too short in Wolff-Parkinson-White, it also can become too long in heart block. Basically this indicates that there's a problem with the AV node. And that can be one of the first places that there's a problem, because it's inside the heart, and it's going to be one of the first places that's subjected to ion imbalances caused by lack of blood flow, because it's going to be the last part to get good blood flow. There's 3 different versions of heart block. There's called 1st degree, 2nd degree, and 3rd degree. Let's look here in lead 2, and you can see that this is a QRST, and the P wave is right here. There's a long delay between the P wave and the QRS, and that would suggest a very long PR interval. Second degree block, I don't think there's examples of this, but second degree block means it's continually extending and occasionally there's a P wave without a following QRS. Third degree block means there's complete separation between the P wave and the QRS. There's a complete lack of communication between the atria and the ventricles via the AV node, so there's a complete block. Next up is QRS Complex, and basically what you're looking for with the QRS Complex is a nice tall, sharp wave. And it can become widened, and that generally indicates some kind of bundle branch block. I think of the bundle branches as basically the highway of voltage down the septum of the heart. It's a quick way to get the QRS moving. And what happens if that's blocked is it slows everything down. I kind of look at it as if you had to close a highway, people would still get where they're going, and you really couldn't predict where they're going, but they're going to get there, and they're going to get there slower. So you'll see a change in the QRS, and it's going to get wider. So if you block the highway down the middle of the septum, which is the bundle branch, the current is still going to flow down the heart, but you're not going to know which pathway, so it might be an abnormal pathway or an abnormal shape. But one thing you are definitely going to notice is it's going to be wider. So this again indicates a bundle branch block. Next up is a long QT interval. One of the things about QT interval is down here you have to calculate it based on heart rate because it's going to shorten as heart rate increases. So you have to do kind of a complex calculation taking into account heart rate. And we can actually see that long QT. Let's go to this lead 2. So this is PQRS, and we have to wait all the way out here until we get to the T. Or maybe the better place to look is down here because there's an extended lead 2. We got a PQRS and an extended T. Now the reason we care about the long QT is because the way the heart normally works is after contraction there's kind of a timeout period called the absolute refractory period, and it causes a rest in heart muscle. Now hopefully when the heart muscle is ready to come out of that timeout, the first one that comes out of that timeout is the SA node or the pacemaker, so it gets to take control again and direct the next heartbeat. Now one of the problems with the long QT is what's actually happening here is we're staying depolarized for a long time. Remember that the QR is depolarization of the atria and the T is repolarization, so this means that we're staying depolarized for that entire time. So these cells are still stimulated. If neighboring cells should happen to come out of that refractory period or that timeout period before this repolarizes, then these cells that are maintaining that depolarization can stimulate their neighboring cells, kind of take over for the pacemaker, and you'll have an ectopic pacemaker or a pacemaker that doesn't belong there. And that's going to be a problem because the normal pacemaker is positioned just right to push blood down into the ventricles and then out of the ventricles. If you move that pacemaker down into the ventricles, you're not going to pump blood in the correct direction. Let's head back and see what's left. Now I'm going to do these two together, normal ST segment and a normal T wave. And basically what you're looking at out here is you're looking at the process of repolarization. So here we've got kind of an abnormal repolarization, or it's even more evident right here. We have a depressed ST. This would be S and T. And what this would indicate, and there's another video on this, it's called stress test or treadmill test. This would indicate that the heart is changing its path of repolarization. There's something that's changing. Now this can happen normally in young people. This can happen normally in certain races. The key difference is did this change from a normal ST to a depressed ST? And that's where you'd want to go to that video. Because what's going to happen in that situation is basically if repolarization is changing, it means certain parts of the heart are not flushing out their potassium, are having difficulty repolarizing, and that's changing the pathway of repolarization. The reason you wouldn't be able to flush out potassium and you change this whole repolarization is because there's not enough blood flow. So generally any kind of change in the ST segment or the T wave upon exertion would indicate difficulty repolarizing, an abnormal repolarization path that's probably tied to the decrease in blood flow, making it hard to wash out potassium. And you can also see it just generally with hyperkalemia. Hyperkalemia again is going to reproduce the conditions of not being able to flush out potassium. There's too much potassium. It makes it hard for the cell to repolarize, and that changes the repolarization pathway. Alright, so that marks the end, I hope, of our 12-lead EKG. It's about an hour in total, maybe about 50 minutes in total. Thank you for listening.